No, ma quel coso non so. Però la cosa importante è che sulla cosa trasmessa non si vede.
No.
No. Vedete, se io partecipo adesso però anche se vede le registrazioni non appaiono.
Allora, come si fa a passare dall'uno all'altra?
4 dita e butti verso l'alto. E ti selezioni l'altro.
Ok. We are back and we can restart. And the second part of this class, we will see how we can combine the differential equations in order to get a higher order one, but which can be solved to get a unique solution for our problem. So the first thing we do is to start, of course, from the previous equations, like these, and we can do it starting from the equation which connects shear force and axial force, and so we can use the first equation like this to solve it for n. And so we can see that n can be solved as a function of the derivative of the shear force with respect to the arc length plus the distributed load along the radial direction. And of course, with the proper sign, and here rho is the radius of curvature. Then we can take the derivative of both sides, and so we can now substitute the expression of dn over the derivative of n inside this equation, and so we can reach a second order equation, differential equation, in terms of t, which is exactly this one. And we see that we get a differential equation of second order in variable t. Now we use the third equilibrium equation, and which is this one. And so we can say that t is linked to the derivative of bending moment. And so if we use this equation, we can take the second derivative of t here. So the basic idea is to express everything in terms of the bending moment. So we can replace in this equation the value of t we have here, and then taking the second derivative of this and replacing it, we will get a differential equation which contains only the bending moment and its derivative. And that is what is done here. So the second derivative of t is this one. Then, of course, the second derivative of t is this expression, which can be substituted here. And so, by combining these two equations, we reach this expression. And so now we have a unique third order equation in terms of the bending moment, which holds for our arch. And so this is still an equilibrium equation which links the bending moment and its derivative to the applied loads. So there is this term which contains the distributed couples and the second derivative of distributed couples, the derivative of the radial loads and the tangential loads. Up to here, we get a differential equation in terms of equilibrium things. So in general, even though we can try to integrate this equation, we generally are not able to know the boundary conditions in case of statically undeterminate problems. So the basic idea is to introduce now the compatibility conditions in order to express all things in terms of these variables. So now we work with a compatibility condition which is this one, and here there is a missing term, sorry, and this links the bending moment to kinematic things, and so we proceed in this way, and we see that the compatibility condition, once we have inserted the constitutive law, is this one. So we can rearrange terms and taking into account the other compatibility conditions, which in the case of inextensibility and beam which cannot be deformed in shear, so this one, we can, of course, use this to substitute again, and so we reach this equation which involves only the radial displacement VR and links it to the bending moment and to the distributed distortions. So from this equation we can solve in terms of m and get the derivative of m. So we reach this expression. This is the expression of m which comes out from here when we solve the equations in terms of m. And so we see that expression of m involves the second derivative of the radial displacement and other terms. And so when we take the first, second, third derivative, we obtain this expression. Of course, this comes out in this simple way because we are considering that the radius of curvature is constant, and so when we have to take the derivative of this term, it's simply 1 over r squared multiplied by the derivative Vr with reference to the arc length, and so on. So combining these, substituting these expressions into the equation of third order of the bending moment, which is this equation 11.7, we at the end reach this expression. And this is a fundamental equation, which is a fifth order differential equation in the radial displacement. And the right-hand side contains known quantities, so are derivatives of several order related to the distributed couples, distributed radial loads, distributed tangential loads, and distributed distortion, angular, axial, and shear ones. So, of course, this is in terms of the arc length. For the arch, as we have seen, everything can be written in terms of the anomaly, psi, which is linked to the arc length by these relationships. And it is easy to see that nth order derivatives with reference of any variable with reference to the arc length can be computed as nth order derivatives with reference to the anomaly psi by simply multiplying by 1 over r at the nth power. So if we make this substitution here and then we get rid of these r at the denominator by multiplying by r to the 5th power, we reach this equation. So it's an equation of the 5th order of the radial displacement with reference to the anomaly, taken with respect to the anomaly, and this is right-hand side. So all what appears in the right-hand side has to be a well-known function of the anomaly psi, and so the solution of this differential equation can be determined as a sum of the homogeneous solution, so the solution of this differential equation for 0 terms in the right-hand side, plus a particular solution of the complete equation. If we now look at the complete, at the homogeneous equation, the homogeneous equation is this 5th order equation. And so by this equation, we get with the usual substitution, so we assume that VR has an exponential form, so it's something like e to the lambda psi. We can then replace here, and we get a characteristic polynomial of this kind. Lambda to the 5th power plus 2 lambda to the 3rd power plus lambda equals 0. So the roots of this polynomial are clearly lambda 1 is equal to 0, and the other 4 roots are the root of the biquadratic equation lambda to the 4th plus 2 lambda 2nd plus 1 equal to 0. And by solving this simple equation, we see that there are 2 double roots, one which is plus I being the imaginary unit, and 2 which are minus I. So replacing into the expression of the exponential and taking a combination of these, we see that the relevant solution is of this kind. C1 cosinus of psi plus C2 sinus of psi plus C3 psi cosine psi plus C4 psi sin psi plus C5, where of course the term psi multiplied by the trigonometric function is a requirement because there are multiple roots. So at the very end, we see that the solution of this problem, once we know also a particular solution, is given. Then we can use this solution, so we know now how it's done VR, and we then can use the expression of once we know VR, we can use this equation, which is a first order differential equation in T in Vt, to get what is Vt. Otherwise, you could simply replace, yes, it's the easiest thing. Otherwise, we could manipulate again this equation to get a 6th order equation in terms of Vt. Anyway, once we have done this problem, we reach this solution in terms of VR. So once we know VR, we can, by the previous equation, detect, integrating this one, detect how is VT done. And so the solution is complete in the sense that once we know this function, we can then compute the rotation, cross-sectional rotation phi by taking the derivative of VR and summing VT. And so we know that expression. And then, of course, we can also get all the solutions in terms of stress resultant N, T, and N according to these equations. So in this way, we can get the complete solution for an arch using only kinematic variables. Of course, these equations must be solved introducing suitable boundary conditions at the ends of the arch, which will allow us to detect, to compute the value of this fifth constant and of the sixth constant, which comes out from the solution of this equation. Okay, so that is for what is relevant to circular arches. For parabolic arches, it is possible to do something similar, but in this case, if we adopt the standard direction of the fixed axis, it is more useful to introduce a new parametrization. Instead of using the arc length, we can use the projection of the arc length along the horizontal and vertical direction. And so using some differential properties, we can see that a general portion of the arch can be written in this way, an infinitesimal one. So the length of the arch is simply the dot product of dx times dx under the square root. And so we can write finally that ds is given by dz multiplied by 1 plus the derivative of y with respect to z, in the sense that we take z as being the independent variable and y as being a dependent variable on z. So we can write down that dz over ds is this expression, and from this it follows that the expression of curvature can be given this form, which involves a second derivative of y with respect to z on the numerator, and in this denominator there is 1 plus square of the first derivative, and this term is 2 power 3 half. So if we call now psi to be the angle formed by the tangent at the axis line with reference to the horizontal, we can see that sine and cosine of this psi can be expressed simply by these relations. So considering that it is dy over dz times dz over ds for the sine of psi, instead cosine of psi is simply dz over ds. And we realize that the first derivative of y with reference to z is exactly the tangent of this angle psi. So what we can do is then to replace the derivative in the equilibrium equation, and it is relatively easy to see that we get these equations involving the trigonometric function of the angle psi. Similarly, we can work with the constitutive equation, with the compatibility conditions, and inserting the constitutive equations, taking again into account that the arch is considered to be inextensible and shear undeformable. So with this system, we can arrive at formulating the equation for the behavior of a parabolic arch. Parabolic arches are important because generally they can be shaped in order to be the funicular of a generic vertical load distribution. It is possible to show that the funicular of load distribution Q has to satisfy this equation. And so if we know how this Q of Z is done, we can see that the general solution can be given this shape. So C1, C2, and the thrust H can be determined by imposing that the shape of the parabolic arch has to satisfy this condition, so that if we place the origin of the system of reference on the crown of the arch, we can simply impose that for the point H, the parabola has to go through this point, as it has to go through point B, and instead that in the crown of the arch, the parabola has to go through this point, through point O. So it's simply requiring it to satisfy these three boundary conditions. And in the particular case where the arch is symmetric and the supporters are the same level, one can see that constant C1 and C2 gets a value 0, and the thrust has this value. So when we know the thrust, we can see that the shape of the parabola is given by this system. And so we can devise a parabolic arch which, for a given value of QV, has only this shape. In this way, we are sure that an arch which has exactly this shape will be submitted only to axial load and not to bending moment. Well, so I believe that now I have finished this part, so if there are any questions, we can answer this question. Otherwise, the next class will be in the afternoon with Professor Fraternali. Okay, so
Vediamo la dimostrazione.
sì.